Assalamualaikum and salam sejahtera. I am NORNAZATUL. I am BINTI AFZAINIZAM. I will explain my bachelor degree project 2 with the title Cutting Parameter Optimization for Rotary Ultrasonic Assisted Machining of Alumina Ceramic Material. My supervisor is PM Dr. Raja IZAMSHAH bin Raja ABDULLAH. According to Power and others in their study, in 2020, alumina ceramic is classified as a difficult to manufacture material because of its high hardness, electrical conductivity, and low thermal conductivity. On the other hand, the rotary ultrasonic assisted machining method has been observed as one of the best suitable methods for the precise processing of alumina ceramic. It can work with brittle and hard materials with mechanical, electrical, and thermal properties. So, in this video presentation, optimization of cutting parameter is investigated to assess surface roughness, material removal rate, and reduction of effective cutting diameter in the end milling of alumina ceramic. I describe some issues that arise during the machining of alumina ceramic with an ultrasonic assisted milling machine. During the cutting process, an edge burr can be seen because when the cutting tool is nearly through the workpiece, the rod breaks away from the workpiece, causing the crack around the whole edge. Cracks on the finished goods are generally unacceptable and must be machined away by either process. After the machining, the most difficult task was achieving the highest MRR while minimizing surface roughness and crack. Assigning simultaneous optimization of these variables in any machine operation can be a useful development in solving real-world industrial problems. Poor surface roughness and crack, on the other hand, are the result of improperly controlled machining parameters. When using USM to cut alumina ceramic, a few issues arise. The advantage of RUM can be effectively utilized by optimizing the alumina ceramic cutting parameters. Next, the objectives throughout this project are as follows. First, to investigate the effect of cutting parameters of rotary ultrasonic assisted machining towards machining performance, which is surface roughness, MRR, and reduction of effective cutting diameter. Next, to know the optimized cutting parameter, which is spindle speed, feed rate, and depth of cut of rotary ultrasonic assisted machining for effectively machining alumina ceramic. Here can be seen in the following slide are among the journals that I used to get the range cutting parameters for my project, as well as the views of researchers to obtain cutting optimization parameters, such as by increased depth of cut and feed rate, provide the optimum solution in terms of MRR. A higher cutting speed with a lower feed rate can reduce surface roughness value, and the surface roughness decrease with the increasing tool overlapping percentage. Now, I will also describe the methodology. Based on this flowchart, you can see my project flow throughout this SEM. So the range value for the cutting parameter was decided by analyzing all the journals. I entered the value that has been agreed with the supervisor into the design expert to get the design of my experiment. I use RSM box pattern, and there are 17 runs to be done throughout the machining process. First, to measure surface roughness, the surface roughness of each machining slot will be measured. The surface roughness is measured 3 times, and the average is calculated. The evaluation length was identical for every slot, which is each is 4 mm. Next, for MRR, weighting will be done both before and after the machining and use as shown formula to calculate MRR. Lastly, the reduction effective cutting diameter was measured with the same length of 1.5 cm at both beginning and end of the slot. Best with the diameter profile without considering chipping because it is impossible for the end mill diameter to increase. It was calculated using the formula initial diameter minus final diameter of the mill slot. USG software was used to define the diameter. Move to result and discussion. This is a picture of the 17-run machining process that I have done. First, we will focus on surface roughness. The combination of run number 3 produced the lowest surface roughness with an average value of 3.93 micrometer. The results showed that an optimal combination of cutting parameters could produce a smoother surface roughness. However, it can be seen that increasing the spindle speed and ultrasonic frequency produce a better surface roughness. High spinner speed and specific vibration frequency may affect the exact tool trajectory by shortening the cutting period, resulting in fewer cutter marks on the machining surface. In the case of feed rate, however, the surface roughness value increases as the feed rate increases. This is due to an increase of thrust forces acting on the workpiece surface, affecting machining stability and thus increasing the roughness value. In addition, both combined actions such as rotating cutter and vibration impact increase the localized stress force on the surface, which reduce the peak height, hence improving the surface roughness value. The following is the sequence from the most significant to not significant factor for surface roughness in ANOVA analysis. It can be seen that spindle speed are the most important factors for surface roughness, followed by feed rate and depth of cut. If we change the slightest value of the spindle speed, it will give a huge change in the value of surface roughness. The normal graph represents the predicted versus actual spot of response and helpful to detect outlier value that the model predicts. It shows that the model generated fit well with the observed value. From the outlier graph, we can see all points are still in the range value and not too far from each other. Through the box plot graph, it can be seen that no proposed transformation needs to be changed. For 3D graph interaction, we want low surface roughness. In the region when the spindle speed is moderate, the feed rate is minimum for interaction graph AB. In contrast, spindle speed and depth of cut are in moderate range for AC interaction. Finally, 3D graph interaction for BC requires a range with minimum feed rate and a maximum depth of cut. Next, for MRR, the combination of run number 11 produces the highest MRR with a value of 216.36. As highest MRR can produce a more precise result. The amplitude of vibration increases with ultrasonic power, which further promotes more effectual removal of swarf and debris through the appropriate flow of the coolant fluid from the machining zone, hence resulted in enhanced rate of MRR. Similar findings have been reported in different investigations carried out on RUM of ceramic materials. For ANOVA analysis, the following is the sequence from the most important to not significant factor for MRR. It can be seen that A is the most important factor for MRR, which is spindle speed, followed by feed rate and depth of cut. Throughout the box plot graph, it can be seen that there is a model transformation that needs to be changed. And for the knowledge of ANOVA analysis and the graph shown earlier is the result after the transformation is be done. This is a 3D interaction graph because we want the maximum MRR. The interaction graph shows AB, which is feed rate and spindle speed. To get the maximum MRR, we need the maximum spindle speed and feed rate range. Next, for effective reduction of cutting diameter, the end mills will wear out as a function of machining time. As the tool wear, the diameter of the machine slot will reduce. Due to that, the difference between the diameter of the starting and at the end of the machine slot can indicate the wear of the end mill. It is revealed that at higher level of spindle speed, which is 6000 RPM, the slot's level induction depth is minimal, further promoting the material to be removed in ductile mode. In addition, material removal in the form of smaller chunks and the presence of sharp edge region also favor the brittle failure of the work, affecting the slot diameter. For ANOVA analysis, the following is the sequence from the most significant to not significant factor for effective reduction of cutting diameter. It can be seen that spindle speed is the most important factor for effective reduction of cutting diameter, followed by depth of cut and feed rate. This is 3D graph interaction. Because we want the effective reduction of cutting diameter is low, AB interaction graph show that the spindle speed need a minimum range and the maximum range of feed rate. The final statistical equation model was developed by ANOVA in terms of actual factor and is presented as shown. Single response optimization was undertaken to identify the appropriate combination of input parameters to obtain the optimal value of the interesting response. For this reason, all the input variables were confined in a specific space by placing the constraint as provided as shown. Application, lower surface roughness value and effective cutting diameter reduction are required, while MRR must be higher. For the ideal solution, the surface roughness and effective reduction of cutting diameter were chosen to be minimized and MRR was set to be maximized. The aim was to set a range for the all input variables, emphasizing that variable will be optimized by exploring the region within the lower and the upper limit. Lower surface roughness with lower effective reduction of cutting diameter and high MR cannot be accomplished concurrently for a specific parametric scenario. While surface roughness and reduction are related to a quality aspect, the MRR is related to the quantity aspect of the RUM process. Therefore, machining capabilities that maximize the different goals must be acquired for industrial purpose. To this purpose, the traceability strategy was implemented for multi-response optimization. In other terms, if the surface roughness is lesser, then the MMR will also be smaller, which is not the optimal case. The consistency of the solution is determined in the sense of closeness of mean to desired target values. A good balance of performance response will reach the desirability value of 1. One with optimal desirability is selected from all the optimal solutions to achieve a good compromise between the analyzed response. Simultaneously, the table outlines the optimized setting of process variable after rounding up. The spindle speed of 1976 rpm, the feed rate of 50 mm per minute, depth of cut of 1.5 mm are the optimal experimental condition for multi-response optimization with the composite desirability of 0.830. Proven those three parameters affect the outcome measurement, it can be seen from the ANOVA analysis that spindle speed is the most crucial factor for the three outputs, which are surface roughness, MRR, and effective reduction of cutting diameter. Hence, the first objective is realistically achievable. Next, we can know the optimized cutting parameters, which is spindle speed, feed rate, depth of cut, of rotary ultrasonic assisted machining for effectively machining alumina ceramic. As for a recommendation, I think it is necessary to select a range value parameter for a more precise to get more precise output value. Other than that, work on improving the optimization value, avoiding human factors influencing the result, and performing output measurement with greater caution. That's all for me. Thank you.